Hello, it's Keith here, and this is lesson 6 of my 6502 assembly programming tutorials. Now we've been over a wide variety of commands and we've now covered most of the mathematical ones we're going to need, but we do still have some more things that we want to look at, and these are more related to ways of using those commands and also commands that we can give to the assembler that will tell it to do things for us. So what are we going to do today? Well, the first thing I want to discuss with you is how we can actually create data within our code. There will be times where we need our program code to read in data in the form of bytes that will be used for temporary storage, or maybe for lookup tables, which is something we're going to look at later, where we store a bank of data and then read from specific positions within that data. So let's have a look at how we can define bytes of data within our code block. So this is the first example I want to show you today. It's very simple. All we're going to do is we're going to dump an area of memory and we're going to define 3 labels here, and we're going to define 4 bytes at each label. Now the first one, we're going to define 4 bytes as individual bytes. So we've got this define byte command here, and in the VASM assembler this allows us to define different bytes separated by commas. So here we've defined a byte that's hexadecimal 1, and then hexadecimal 2, hexadecimal 3 and hexadecimal 4, and that's just fine when we want to define individual bytes. Now there will be times where we need to define words, and these are of course pairs of bytes, and so we can do that as well using the DW command to define words. Now you can see here I've defined F1, F0, but we'll see how that actually appears in memory later, because you've got to remember this is a little endian machine. As well as bytes and words, we may want to define banks of data with specific lengths. Now we can use the ds command to define a sequence. If we just need a block of blank memory, for example 128 bytes, we can just use the command ds with 128, like this. But if we need a bank of specific bytes, for example we may need ff for some reason, or in this case I've defined cc, we can do our number, which is the number of bytes to define, and then the byte to fill with, following that separated by a comma. So let's see the result of these 3 definitions here in memory. So here you can see the memory that we've defined here, and we're dumping the bytes area, and we're just dumping a few lines of memory here. So you can see our 1, 2, 3, 4 defined exactly as we'd expect them, but when we got our F1, F0, we can see here the 2 bytes are backwards. Now hopefully at this point you know why that is. It's because the 6502 is little endian, so the least significant byte comes first and the most significant byte comes second. So F1, F0 is stored in memory as F0, F1. It's important to remember, but as I say, you should really know that by this stage. Here we've used the ds command to define 3 bytes, and we've filled them with cc, and you can see those 3 bytes here. And then we've defined 1 byte without specifying what we're going to fill with, and that's been filled with 0 here. And these 4 bytes here are just other data. They'll be the next part of the program code actually. So this is how we can define bytes within our program area for various purposes, and we're going to need that as we look at the later examples today. So what can we do with these defined bytes? Well, one of the things that will be very important for your programming is something called lookup tables. There will be times in our programming where we need a set of values, and we will need one of those values pulled by an index. So for example, you may need a bank of colours and you need to pick a particular colour, or you may need a bank of addresses and you need to load in an address from that lookup table. Now, in the example today, we're going to have a look at using a sine wave. We're going to define a lookup table of 16 sine wave positions, and rather than the ridiculously complex method of calculating a sine wave, we can just read in from that lookup table. That'll be very easy for us. So our lookup table is here, and you can see there are 16 bytes here, and the values go from 0 to 255. Now what are we going to do with this sine wave? Well, we're going to show it to the screen. I think at this point, if we have a look at the result and then see how we get to that result, it will be a bit more clear. So you can see the sine wave drawing slowly here. Now it's very crude, of course, we're just plotting x's here because we don't want to use any graphics, but you can see we've basically got a sine wave here, and this has been created by converting these values to screen coordinates. So what have we actually done? Well, first of all, we are using the 16 entries a single time within the lookup table, and so we're defining x as 16. Now this lookup table will go from 0 to 15, which is why our first command is decrement x. We're then backing up x here while we do our sine locate command. This uses the value in x as the y position, and it uses one of the entries from the sine wave as the x position, and it draws an x in that position. So that's what we're doing here. We've got a delay command, which is just slowing things down so it looks a bit interesting. And then we're decreasing x, seeing if we've got to 0 yet. And if we haven't, we're looping again. So this will do from 15, because we immediately decremented, to 0, including 0. Our sine locate command is quite straightforward. At this point, we'd pushed x into a, and then we are transferring a to y. And the reason we're doing this is because we want the y position for our locate command to be the entry that we're reading from the sine table. Now the 6502 is very good at this kind of looking up entries in tables and things, and we can use the indexed addressing mode of the 650 to do this for us. So all we need to do is we need to have this sign label here, which points here, and then we use X as an offset to that sign table. So as long as X is less than 16, then we will read in from one of these entries here. The only problem with this is the entries are too high. These are going from 0 to 255. We want an entry to go from 0 to 15. So what we need to do is we need to shift all of the bits to the right 4 times. And that's what we're doing here. So that by the time we get to here, the value will be from 0 to 15, which is adequate for an X coordinate. And then we can just use that in a locate command. Now, of course, we could rem out one of these and we could use the full width of the screen if we so wished. And you can see now the wave is wider, but that's not really anything to do with lookup tables, so we'll just leave it as it is. So you can see here that we can have a table of data that we don't want to have to calculate and quickly look up values with LDA here and by using the indexed addressing with X here. Now the only thing is here, of course, is that X can only go up to 255, so you couldn't have a 512 entry lookup table here if you've even got memory for that. But if you wanted to do that kind of thing, you would have to use some kind of 0-page temporary values and look up from that 0-page address. So there would be, of course, ways of doing it. And you'd want to look at the way we looked at addition of 16-bit numbers last time, because you'd need to calculate a 16-bit address in that case. Now in that case we've used a lookup table and each entry in the table has just been a single byte, but there's no limit to the number of bytes an entry in a lookup table can contain. There's no reason we can't use 2, 4, 8, 16 or anything really bytes. The only thing is if we're going to use this indexed addressing, then we are going to be limited to a maximum of 256 bytes within our lookup table. So if each entry is 4 bytes, then our lookup table is going to be limited to 64 entries. Of course in that case we would need to quadruple X before we read it in. And so we could use some left shifts to do that. Now that's the concept of a lookup table, but there is a special kind of table that's often known as a vector table. This is a table of calls. What's this for? Well, in the case I'm going to show you today, we're going to create a table of simple commands, and then we're going to call one of those commands just with a single number, a single byte. So we will call command 1, command 2, command 3, and these will execute different pieces of our code. There's various reasons we might want to do this, and we'll discuss those later. So this is going to be quite a long example, so you'll have to bear with me a little bit, but it is quite important. So we're going to create a command called vector jump. This is going to execute a call within a lookup table, and the entries of the lookup table are going to be memory addresses, so they're each going to be a word, 2 bytes, and we're going to take a single value in the accumulator to call one of those commands. So if we wanted to call command 1, then we just load A with 1 and call vector jump. If we want to load command 2, we load A with 2 and call vector jump. Now let's execute this just very simply with those 2 commands here. Now you can see what's happened is we've printed the word cake and we've actually started a new line. Now I've created symbols here to make it more clear within the code, and we can actually just replace them here. So if I just copy the cake command here, and then if I just put the dash command in here, we can now execute this and you can see the result is as we expect. We've got the word cake and then we've got a dash here. So we're executing command numbers from here via this vector jump. And you can see here the vector list is what's actually defining what each numbered command does. So command 0 is here and it loads A with this dash and then prints it. Command 1 is a new line command. Command 2 prints the word cake, and command 3 prints the word cheese. So if we run our program again, you can see we were printing the word cake followed by a dash. But if I change command 0 here to run command 3 and run this again, you'll see we now have the word cake cheese. This is because I've changed the actual pointers in the vector list, and that is what is doing all of the work. Now, of course, the actual work of printing things is done by these labels here, but what actually defines which label to execute is this vector list here. So let's take a look at the code that actually does the vector jump. Well, it's very straightforward. When this code is executed, the command number is in the accumulator, and all we need to do is we need to shift that to the left once to double the number. You see each entry in the vector list is 2 bytes, so entry 0 will be at offset 0, entry 1 will be at offset 2, so we need to double it. And then we load in from the vector list offset by X here, and then we store that into L, and then we load increment X, we load in another entry and we store that in H. We load into L first because of little endian. These are 2 entries within our 0 page. Now we do an indirect jump to the address ZHL, and that will execute the vector call that we want. Now, if you're not familiar with my tutorials, I tend to use H and L definitions, and I use these as 0-page offsets. The exact address of these will depend varying on the system, but basically I'm using entries in the 0 page to kind of simulate the functions of the Z80 registers that I'm more familiar with, because typically I'm a Z80 programmer, so that's the way I find it most easy to work with. But if you're writing this yourself and you don't want to do it like that, that's fine. You could just change these to hexadecimal 10 and hexadecimal 11, and this would be hexadecimal 10 or something like that, and that would work just the same. Now, what's the point of this? Well, the most simple reason you might want to do this is, let's pretend you have a module that you're loading into your program and your program is executing that module. Now that module might change over time, you might add extra functions to it or change the functionality, or even in some cases the functionality may need to be different depending on different systems. For example, maybe that module actually handles the loading and saving of files. On a tape system you'll need one set of commands, and on a disk system you'll need another. Now that module may change very, very wildly, so you won't really want to call particular label addresses within that module because they may move around or they may disappear. But if you pass a number to that module, you'll be able to then jump very quickly into those different areas within the module, and you'll just have a common, what's known as a jump block, which is a set of jumps or a single jump at a fixed address, usually at the start of the code, that will actually handle that vector array. So this is a way you can very easily allow your code to be very configurable, and also you're able to run commands just with a single byte. Now the example we've seen there was very crude. We just loaded A with the value and then jumped to the vector jump. But if we have a look at the rest of the code, we'll see we're doing something much more clever. Now what we're doing here is we're loading in from something called a command list, and this command list is here. And these are all of course individual bytes, but I'm using these defined symbols here. To actually specify which byte to use, and the end of the list is a number 255, and what we're doing is we're starting x at 0, so reading in the first entry in the list here, and then we're sequencing through the list, and each of the bytes we read in that isn't 255 we're using as a command for the vector jump, and we're looping around here processing all those commands. So if I just rem these lines out here and just run this program now, you'll see we've printed cake, cheese, cheese, hash, cake, and you can see here cake, new line cheese dash cake, and then the end of the commands. So effectively what we've done here is we've defined a scripted language that can print strings of text using lookups. And of course the benefit for this is that if we now needed 1,000 entries to this list, we could do that. I mean, okay, we'd need to change from using the X register here, but we could do that, and it would only take 1,000 bytes. If we did 1,000 calls, it would take 3,000 bytes. So we've effectively saved a lot of memory, and we've also allowed ourselves the configurability to switch the functionality of these commands, and everything else will continue to work just fine. So that's really the power of a vector list. It's saving memory, it's enhancing functionality, and it's protecting us so that we can change our functionality later on without having to change all of the other code. Now in my Z80 game Chibi Akimas, I originally used a jump block, but as the game became bigger and bigger, the jump block really became quite cumbersome because each entry was a jump command, which is a single byte, and an address, which is 2 bytes. And when you get to like 50 or 100 entries, all of those jump commands start to really add up. But a vector list like this, you've only got the overhead of the actual vector jump code here, and that will do all of the work for you, and you really don't then need to add any extra waste in your vector list for the jump commands, because there are no jump commands. So there we've had a look at a vector table, but I want to show you an even more advanced version of that vector table, and we're going to do some more tricks, and this is something that's known as self-modified code. Now this may sound quite daunting, but it is quite important to 8-bit programming if you're trying to program for speed. An important thing to know about self-modifying code, apart from the fact it can be a bit tricky, is it will only work if your program is in RAM. If you're working on a system that's running from ROM, for example the Atari 5200 or the Nintendo NES, then you're not going to be able to do self-modifying code, which is why I'm only mentioning it to you at this stage and not really recommending it to you. What self-modifying code does though is it reprograms part of the code. This will typically take one of 3 different approaches depending on how adventurous you're being. This could be changing the destination of calls or jumps so that they jump to different places, and this can save us from having to do conditions. If the first time we do a loop we jump to label A, and the second time we do the loop we jump to label B, well, why not change the label to label B in the code the second time we do the loop? This will allow us to avoid doing any kind of condition, and it can save us some time. Another time we may want to do self-modifying code is to get back values. Let's say we have a piece of code that needs to read in the position of the player, for example. Rather than loading in the position of the player from a memory address, why not just modify the code and actually insert the new value of the position of the player straight into the load command? This will save a bit of time, and it will save the memory that was previously storing that data. An even more advanced form of self-modifying code is where we completely reprogram commands. This could be, for example, changing an add command to a subtract command, or it could be changing a jump to a set of no operations to remove its functionality altogether. But today we're going to have a look at some ways we can change the previous example using self-modifying code that may be worth us looking at in our own programs. So here's the program again, and the functionality is basically the same as we saw before, but it's had some important changes, and let's have a look at them now. So what's changed? Well, the first thing you should notice is that this vector jump command is no longer using the indirect jump here. We were using this jump in bracket ZHL, and now we're not. Now we're just using a jump to test command 0, but we're not using a jump to test command 0. Do you see this label here, this self-mod label? And this self-mod label is being used here, and we're subtracting 2 from it. What we're doing is we're loading a byte in from the vector list and then storing it to this address here. Effectively, we're changing test command 0 to point to one of the other addresses in this vector table here. We're changing the bottom byte of this jump to effectively change the jump to one of the other labels. Now this is beneficial in 2 ways. We're no longer using that HL 0 page entry, so we're saving a lot of space there, and we're also no longer doing both bytes. We're only doing a single byte here, and also the jump command will be faster. That does, however, pose a problem. We're only setting the low byte of the memory address in this jump here. Well, how can we get away with that? Well, we can only get away with it is if all of the possible destination commands are within the same byte. For example, they could all be in the memory address 1A00 to 1AFF or 1C00 to 1CFF. But if command 1 was at 1AFE and command 2 was at 1B01, then it's not going to work because we'd need to change both bytes. What we need to do is pad the code with zeros until we start a new top byte. And the way we can do that is with the align command. Now the align command will vary depending on your assembler, but on VASM, the way the align command works is we define the number of bits we need to 0 before the next command commences. So by saying align 8 here, we're telling the assembler pad the code with zeros until we start a new top byte in our address. And this means that as long as this area of code here is less than 256 bytes, they will all definitely be within the same top byte memory address, and that means we can safely self-modify this just by changing the bottom byte. So that's how we can use the align command, and the align command does become very important if we're trying to use things like self-modifying code or lookup tables in some cases where we're trying to save time by not changing the top and bottom bytes of things. There is a second example of self-modifying code here. It's not as useful, but I thought I'd put it in anyway. So you'll see here we are having to back up and restore the X value. Now before we were using a push and a pop here, but this time I decided to play around a bit, and rather than doing that I'm using a store command and a load command. So the store command here is storing to xrestore plus 1, and you can see xrestore plus 1 is here, and then what this is doing is it's reprogramming this byte here with the new value of X. So we're effectively backing up X by using self-modifying code here. It does have to be made clear at this point that when you're doing self-modifying code, you need to understand what the actual bytes that your commands are going to compile down to and how they work. I know for a fact that LDX #0 compiles to 2 bytes, and the first byte is the LDX command and the second byte is the value for that command. If I didn't know that, or I loaded into the wrong address, I would corrupt my code. And in the same way, I know that a jump command is 3 bytes and that the address here is in little endian, so the part of the address I want to change is the first byte, so I have to subtract 2 from this label here. Alternately, I could have put this label here and added 1 to it, but I tend to put them at the end. Now all of that's very confusing obviously, and the thing I want to tell you about self-modifying code is it might not be for you at all. If you're doing work on the Nintendo NES or one of the systems that's ROM based, this is probably going to be something you actually want to go into avoid. But if you're trying to write the fastest game possible or the most optimized memory-wise game possible, this is going to be something you're going to have to look at. When I started writing my Z80 game Chibi Akamas, I didn't understand self-modifying code, and I thought I'm not going to need that, I'll just avoid that. But as I started programming things and trying to get the speed as fast as I could, it became almost natural that you had to move to and wanted to move to self-modifying code, because you started to see the inefficiencies in your code and you started to see the way self-modifying code was going to allow you to get around those efficiencies. So it's another thing I'd suggest you just to put at the back of your mind and don't worry about too much today, because the day you do need it, you'll probably realise how it works and why you're going to want to use it. Okay, so that's all I wanted to cover today. We've done some really advanced commands today, and there are some more commands relating to interrupts that we've not covered yet, but to be honest, for basic programming in the kind that we've used in these tutorials and in GRIME 6502, you've actually seen all the commands you're probably going to need at this point. So I think hopefully you're now feeling fairly confident with the language. We're going to continue some more. There's some more stuff I do want to go into in depth in the 6502 assembly itself, and also I'm going to start doing the platform specific series, which is where we actually start to look at individual machines like the NES and the Commodore 64, and we start to discuss how the hardware works and how we actually want to address that hardware to make the graphics work the way we want, and the various options that are available to us for making sound, reading joystick controllers and things like that. So I hope you're going to join me for those series, and also of course check out GRIME 6502, and if you're interested in other platforms as well, I've got Z80 tutorials and 68,000 tutorials, and there'll be lots more tutorials coming in the future. So I hope you'll stick with my channel, and I hope I'll be able to show you lots of interesting things here going forwards. Thanks for watching today, and goodbye.